In this lecture and a few more lectures to come will be analog filter design. So the motivation for analog filter design are twofold. One is that in digital signal processing of analog signals, we do require low pass filters at the front end and at the reception end. In between we have digital signal processing of analog signals. Okay, so in the front end we need a low pass filter, and this low pass filter is an analog low pass filter. Similarly, once you do the processing at the receiving end, also we need again analog low pass filter. Okay, so at the front end, to constrain the bandwidth, okay, the purpose of the front end low pass filter is to constrain the bandwidth so that the requirements of the sampling theorem are satisfied. Okay, you recall from the previous lectures and from the previous course that sampling frequency must be at least twice the highest frequency content of the your input signal. Okay, so therefore this low pass filter constrain the maximum frequency. It will not allow more than this f maximum, so that you can employ sampling at the in between blocks. And similarly at the far end, the receiver end, to get rid of high frequencies from the digital to analog converter. Anyway, you are going to put a D to A converter at the output stage, so the output of D to A converter contains high frequencies. So to get rid of high frequencies from the D to A converter, we need to put again one more low pass filter. Okay, so this is the first motivation, that we need to know about the low pass filter, analog low pass filter. I mean, we should know about analog filter design. And the second motivation is that our IIR filter design, one of the most important and useful in practice, is based on analog filter. Okay, so this IIR filter design is designed by using analog filter design. Okay, so IIR filter design is based on analog filter design using a transformation. Okay, in analog filter we design in the ES domain, Laplace domain. Digital filter we use Z domain. Okay, so we need to move from analog domain to digital domain. Okay, so S domain to Z domain. So IIR filter design, this one of the IIR filter is one of the most important filter and useful in practice, and this is designed using Z domain, and we have to move from Z domain to we have to go to the Z domain from S domain. Here analog filter is designed in S domain. So S to Z we use a transformation. Okay, so there is a transformation procedure that we will see as we go along. So using the transformation, we will move from analog filter design to digital filter design. That is very easy process. In fact, instead of directly designing IIR filter, first you design analog filter and then you do the transformation. Okay, so in the first step, we get the specifications of IIR filter. Okay, and then you have to convert this into digital normalized frequency specs. Okay, you convert them to an analog filter design specs, design the analog filter, and then go back to the Z plane through the S plane. Okay, to the Z plane, S plane to the Z plane transformation. So the motivation for analog filter design discussion in a DSP course are twofolds. Okay, so one is we do require analog filters at the front end and in the far end. And second, a major part of digital filter design is based on transformation of analog filters. So it also is a fact that a discussion of low pass filter is adequate. Okay, why? Because a low pass filter can be converted into any other kind of filter. Okay, any low pass filter can be converted to any other kind of filter. I mean, you can convert into high pass filter, you can convert into band pass filter, band stop filter. So once you know how to design a low pass filter, that's enough. So there is a transformation technique, and you, by using that technique, you can convert the low pass filter into high pass filter, band pass filter and band stop filter. So it is suffice to know how to design a low pass filter. So that is the only important thing one should know. So once you know how to design a low pass filter comfortably, then it's merely a simple transforming technique, that's it. Now as far as this low pass filter is low pass filters are concerned, we will concentrate on two types. There are two types of low pass filter design. The first one is Butterworth method, and the second one is Chebyshev method. Okay, because in most of the practical cases these two types suffice. The most optimum filter is of course the elliptic filter. This is the most optimum filter. But the problem in elliptic filter is that the design requires numerical computation in almost every cases. It is very difficult to tabulate elliptic filters, and no elegant mathematical formulas are available. And therefore in most cases digital signal processing engineers appeal either to the Butterworth or to the Chebyshev. Butterworth is the simplest, but it may involve a little more cost than a Chebyshev filter. We will discuss both of them. Okay, this guy is the simplest one, but implementation wise cost will be little high. Okay. But Chebyshev filter is a little difficult, but implementation wise cost may be less. Okay, but anyway we will discuss both of them. In low pass filter we also concentrate on only one kind of filter. Okay, only one kind of filter, the so called all pole filter. All pole filters. That means the filter only has poles in the finite region of the S plane, because we are discussing analog, right? Analog means in the S domain, so it has the poles in the finite region of the S plane. And is that the statement correct? That means doesn't have any zeros. Okay, there cannot be a filter without zeros. Okay, yes, we will be having zeros, but that zeros will be cancelled with the poles. Okay, so the number of zeros and the number of poles should be the same for any transfer function. So there are zeros, but but those zeros are all at infinity. Now we will consider capital H A of S. Okay, this is the transfer function, and because we are considering filters, and therefore all pole low pass filter, all pole low pass would be some constant in the numerator divided by S to the n plus A suffix n minus 1 S to the n minus 1 plus so on and so forth plus A1S plus A0. So this is the general form of all pole filters. Okay, because if you solve this, you'll get a poles, and the numerator you don't have any poles, you don't have any factors, sorry. So in deviation from digital filter transfer functions, if you remember, in digital filter transfer functions we always write the constant term, this constant term, as unity. I'm sorry, not this constant term, this constant term. Okay, so here in this case we will write the coefficient of the highest power as unity. Okay, you always make sure that the highest power, the coefficient of highest power has unity. Okay, because we will write the poles as S minus Pi. Okay, so the continued product of S minus Pi, where I goes from, let's say, 1 to n. For example, if you have S squared plus 5s plus 6 is equal to 0. Now look at here, the coefficient of the highest power is 1, right? So you can write this this constant is the product of the poles. Let's say there are two poles, it is a second order equation, so P1 and P2, and this guy is nothing but P1 plus P2. Okay, if you solve this equation, then S is equal to minus 3 minus 2, so the poles are P1 is equal to minus 3 and P2 is equal to minus 2. Therefore you can write S minus Pi, continued product of I is equal to 1 to 2, so that is S minus minus of minus plus, then this is 3. You can write like that. So you can write as a continued product of two factors, S plus 3 times S minus 3. Okay, so that is the reason we always write the highest power has a coefficient of 1, and therefore the lowest power, the constant term. Okay, where is the constant term here? This A0 is the constant term, will be simply the product of Pi's. Look at here, S squared plus 5s plus 6. The 6 is nothing but the product of the two factors. Okay, product of Pi's, product of P1 and P2. So so you should write in this format. Okay, if I if I take a 1 second, my pen is not working. Okay, look at here, there is a minus sign. Okay, if I take this as S plus Pi, then A0 will be the product of will be the continued product of Pi's. Okay, instead of writing S minus Pi, if you write S plus Pi, continued product of I is equal to 1 to capital N, then what is your A0 in this expression? A0 is going to be P1 P2 up to Pn. So what about An minus 1 will be? What will be An minus 1? Sum of all pairs. See, this 5 is the sum of two factors, right? P1 plus P2. Similarly, this one An minus 1 is sum of all pairs, P1 plus P2 plus P3 plus and so on up to Pn. Therefore, our aim is to find an HA of S, which is some constant in the numerator divided by the denominator polynomial that I am going to denote by d of s. Okay, what is d of s? D of s is of the form s to the n plus a suffix n minus 1 s to the n minus 1 plus and so on so forth plus a1s plus a0, in such a manner that the given specifications are satisfied. So what are the given specifications for a typical low pass filter? If you take a typical low pass filter, you have the pass band, So the magnitude is 1. This is magnitude of H, and there will be some tolerance in the pass band. The tolerance is delta p, and this frequency is omega p, pass band frequency. Okay, pass band is typically specified from 0 to omega p. So omega p is the pass band frequency, and this is your analog frequency omega. Okay, so we use capital omega for analog angular frequency. Okay, so this I can write as h suffix ea of j omega magnitude. So the stop band will start somewhere here. It goes like this, and this is omega s. From omega s to infinity, this is called a stop band. Okay, so let me write down here 0 to omega p pass band, and omega p to infinity, this is stop band. And what about in between omega p to omega s? The difference between omega p and omega s is the transition band. Omega p to omega s is called transition band. So if you are designing a filter, this transition band should be as low as possible. Okay, then there is a tolerance, let's say delta p, and this height is delta p. So what about this point? This point is going to be 1 minus delta p, where delta p is the tolerance in the pass band. So these are the specifications. Okay, so one should remember this. Similarly, we do have tolerance in the stop band. So this is delta s, tolerance in the stop band. Okay, so these are the specifications. So you will be given omega p pass band frequency, then stop band frequency, then delta p and delta s. These 4 values will be given. So typically what will be specified is omega p, omega s, delta p and delta s. From these 4 specifications, you will have to determine an HA of s which satisfies these specifications. You find a transfer function which satisfies the given specifications. This specification of the satisfaction of specifications also has to be explained. See, you may not be able to exactly satisfy these specifications, but to some extent, approximately, you can satisfy. Okay, you can take liberties with the stop band, but not with the pass band. Okay, many of the textbooks say to the contrary, but the practical design experience is that if I take liberties with the pass band, you spend more man hours. Okay, you spend more engineer hours in designing the filter. The pass band is sacred. Okay, so do not take liberty on pass band. Okay, but the stop band you can take liberty. Liberty means what? You can over satisfy in the sense what? You can reduce attenuation to this level. See, originally the attenuation was here. You can make it low, no problem. Okay, that's what we mean by liberty in the stop band. But you should not reduce the magnitude from this level to this level. That is bad. Okay, over satisfaction in the stop band is very good. Over satisfaction in reducing the transition band is very good, but over satisfying in the pass band also good, but it should not come down, it should go up. So that's what typically the design engineers will try to do it. Okay, for example, this is my omega p and omega s. So this is the point of stop band. Now if you do over satisfaction, that means if you somehow bring this point to here, then you are a good boy. Okay, that means you over satisfied the stop band. But instead of bringing this point to here, if you bring this here, then you are bad. Okay, don't do like that. In case if say let's say omega p is equal to 4000 or something, if you reduce, then you lose your content, frequency content, you lose your information. So over satisfaction in the reducing the omega p to the left hand side is not good, but bringing this omega s to the left hand side is good, very good. So our job is determine an HA of S which satisfies these specifications. Okay, so if my stop band starts earlier here, I'm happy, isn't that? So always we try to over satisfy in the stop band, and don't take any liberties in the pass band. Okay, so that's it. So in the next lecture, with this introduction, the next lecture we will discuss the Butterworth filter. Okay, so let me stop at this point. Thank you very much.